Okay, good morning to all of you. And just let me go to the full screen. Yeah, here we are. Right. This is where we had stopped. We had seen that the holding time of every state that has an exponential distribution with a parameter possibly depending on the state. So the exponential distribution has a close connection with continuous time Markov chains. So such processes, the what we had called as continuous time Markov chain on with state space Z, sometimes are called so-called Markov pure jump processes because transition between states is through jumps. Okay. So first, now we look at the important object, which is called transition probability function. You know, in the case of Markov chains, discrete parameter, we had transition probability matrix. So a similar role here is played by transition probability function, and the definition goes as follows. Let xt be a time homogeneous continuous time Markov chain with state space capital Z. So for every time point t and s and elements ij in the state space, then p sub ijt. So there are three variables. You will see the reason now. So supposing you were to include s also as a variable, then it would be probability x t plus s equal to j, given that xs is I. That is, given that at time s the chain is in state I, the probability that at time t plus s the Markov chain moves to j. Since the chain Markov chain is assumed to be time homogeneous, this probability is same thing as probability xt is in j, given that x0 was at I. So because of the time homogeneity factor, one has been able to, this is here, this depends on only on the time difference between the two time points. And the time difference here is t. Had it been non-homogeneous, it's not time homogeneous, then one would have had to incorporate s also here. But we are not considering such processes at this stage. So this function, this is function as ij and t, that is p sub ij at t is called the transition probability function. So for you can easily see for a fixed I and a fixed t as a function of j, this has properties of probability measure on a discrete space. Okay. And corresponding to this function, there one has an important class of equations. Please note it down. It's called Chapman-Kolmogorov equations. We had also indicated this in an exercise, I think, in our earlier course. But there, that role was basically that what is it? The two matrices get multiplied and so on. So here it is. Okay. So for the result says this for time points s and t and space points I and j, p sub ij t plus s. So that is by definition, you see that it is probability x at t plus s is in j, given that x0 is at. So that is same thing as summation over all the elements in the state space. Let's say P sub ik t multiplied with pkjs. That's very intuitive because if it is going to state j in time t plus s from state I, that at time point s, it must have passed through some k in z. I mean, that is if you take, sorry, yeah, that would be here. If you take s as having been that visited, s is first, or rather the first s points and then the next t interval in the time axis. Here it would be, let's say you are considering t as the intermediate time point and t plus s. For example, this is pretty obvious if you try to draw some kind of a sample path. All the paths which are starting from I at time 0, they have to reach j at t plus s. And therefore, in between the time point t or time point s, they will have to go through some point in z. I mean, intuitively, it's very obvious. Even proof is very simple. So since it is a continuous time Markov chain, you can easily verify. Please note it down. Yeah, the left-hand side, Pij t plus s, that is by definition of our transition probability function. It is this object. So just take the definition of conditional probability, then you have this. And at the intermediate time point, let's say yes, it has gone through some k. So you split the numerator here into this disjoint events and take the sum of them. That is, this event in between, you write xs equal to k. At time s, it must be some k. Now, this is the probability of this event intersection this event. So you can write this probability of this intersection as probability x t plus s equal to j given these two multiplied with probability of the denominator, this thing as the denominator, or sorry, not denominator, multiplied with that. So coming from this step to this step, we have basically used the probability A intersection B is equal to probability A given B multiplied with probability of B, where A is this event and B is this event. So what got cut off here is that is just probability xs equal to k and x0 equal to I. And now in this conditional probability as xt is a continuous time homogeneous continuous time Markov chain, that object is precisely this. And what is left here is this one we have just retained it as it is. And that by definition is precisely P sub IKS. And this is PKJ. So in a similar way, you can do the other thing. It's a very simple thing. It is just that these things were formalized and these have very important implications. That is why that such a simple family of equations has got a name. Chapman-Kolmogorov equations in an honor of those who were instrumental in unearthing the importance of this aspect. Quite a few results which bear somebody's name might actually be very simple. It's just that they had the uncanny intuition to observe that that becomes important. And expound on its importance, the basic nature. You will see one such soon. Please note it down. The discrete time chain, which we had seen last semester, I think if you refer back to your notes, it will be somewhere. If it is not there, it may be in one of those problems. Basically, that p power m plus n is p power m into p power n. That's the same idea. Okay. Now we will consider an important class of continuous time homogeneous continuous time Markov chains taking values on Z. These are the so-called birth and death processes. On birth and death processes itself, there are a lot of books. It's a very important class of processes, but unfortunately, we may just have a glimpse of such things. One type of process which is very important, Poisson process, we have looked in fairly good detail, but hereafter it will be kind of only a just a glimpse. So let's straight away get to the definition. The birth and death processes, I mean, the terminology is rather suggestive. So, yeah. So in this case, we take the state space to be non-negative integers. Of course, since we are calling it as birth and death processes, the assumption is that if the population level at that stage is 0, there cannot be any death at that stage. It has to increase and then only a death can happen. That's the reason. You can also have birth and death processes on the entire non-negative, entire integers. You interpret birth and death in a simpler fashion. So let xt be a time homogeneous continuous time Markov chain with state space S, that is non-negative integers. Let Pijt denote the transition probability function of this Markov chain, continuous time Markov chain. Now this transition probability function, suppose it satisfies certain properties, which we will list below. the first property. Let us say this here, this h is considered to be a small positive number. That is small time, a small interval of time. So an interval of 0 to h would denote as interval of small length. Let's say the probability of reaching I plus 1 from I in a small span of time h, that is roughly proportional to the length of that interval. In this sense, it is lambda I times h plus small order h. That is whatever thing is the remaining here, the probability that goes to 0 faster than h, in the sense that OH term divided by h goes to 0 as h goes to 0. You have seen this notation earlier. Small order h. And of course, the rate, it is proportional to that length of the interval, and that rate, infinitesimal rate, can depend on I. Since we are calling these things as birth-death processes and so on, and these things, what is going to come next, you can easily guess. In a similar fashion, probability of reaching I minus 1 from I in a small span of time is again, that is one thing less, is again proportional to the length of that interval, and the proportionality constant is mu I, that can depend on the state I. So that plus OH. Of course, this makes sense only when I is greater than or equal to 1. Because if I equal to 0, it cannot go below. So that is why it's different. Then we allow for the possibility that in a small span of time, the process can go from I to I itself. In between, it might have gone to some other state, but still, it doesn't matter. The thing is, we are saying this probability is add these two probabilities and 1 minus that, basically. If this and this are small order h, plus this thing, this sum will also be small order or h, that all is incorporated here. This is the third assumption. Next. At the starting point, time 0, Pij is delta Ij. That is, there is no instantaneous jump. For any jump, there has to be sufficient, it cannot, from I, it cannot suddenly immediately move to some other state. That would also sort of contradict your right continuity property of the sample points. Then fifth assumption, mu0 is 0. That is clear from here also, in the sense that when this is mu, the mu parameters, they are indicative of the total this thing, I mean that state going in the negative direction. So if the process is at 0, you cannot go to the left. Otherwise, you assume that all the lambda i's and mu i's are strictly positive. Of course, this is a kind of simplifying assumption. There are also, you can consider cases where that this is not true, but that is going to be more of a nuisance. So such a process is called a birth and death process. That is, this thing increasing by 1 may be called a birth, and the thing reducing by 1 is called a death. So these parameters, lambda I and mu I, these things are kind of infinitesimal rates. So the lambda i's are called infinitesimal birth rates, and the mu i's are called infinitesimal death rates, depending on the current size of the population, namely I. Please note it down. Okay. So, a simple exercise. Show that our good old friend, time homogeneous Poisson process is a birth and death process. Of course, clearly, but in Poisson process, there is no death. Next, we will show how the Chapman-Kolmogorov equations can be used to derive a set of ordinary differential equations satisfied by the transition probability functions of a birth and death. ODEs means ordinary differential equations. So since the state space is this, for positive, time points t and h, and I and j in the state space, but let's say j can be any element in the state space, whereas I we want it to be greater than or equal to 1. We will derive something. The case I equal to 0 will be taken care of subsequently. So we will now derive a set of ODEs for this situation when I is greater than or equal to 1 and j is greater than or equal to 0. All these things are kind of suggestive. Generally, we have been using H for small amount, small quantity, small positive, and T. So we will say something using Chapman-Kolmogorov and then let H go to 0. So that is how one obtains ODE. We have already done such a thing when we when we derived the time homogeneous Poisson process from certain basic principles, postulates. We call it N1 to N6. Okay. So P ij at t plus h. So it is this. This is where we are using the Chapman-Kolmogorov equation. And here what we have done is the time interval 0 to t plus h, we have divided into 0 to h and h to t plus h. And h to t plus h, whatever is the thing behavior, that is captured by this function itself because of time homogeneity property of the process. Okay. Here, k varies from 0 to infinity. That is the state space. This is the state space. So you can take the thing k equal to I minus 1, k equal to I, and k equal to I plus 1 separately. Those three terms you put separate. And all the rest you put here. So when you put k equal to I minus 1, here you get p sub I to I minus 1 h, p I minus 1 to j t, k equal to I means p I h, p I j t, and similarly k equal to I plus 1. So for example, what this means is at time h, the process has come from I to I plus 1. And from h to t plus h, it travels from I plus 1 to j in a span of time t. So all the PIKs, PIK t is less than or equal to 1 because this is probability. The probability of some event. So each of that is less than or equal to 1. So therefore, we just want to show that this summation, this huge thing is very, very negligible. That is, it is small order h. So you take this. So since each pkjt is less than 1, all these things are non-negative. This is less than this without that thing. And since this thing involves only all the terms other than these three, use property 3, I think. This is going to be, this 1 minus these things. It is, here you are not using property 3. It is just using the straightforward this thing of PIKs, PIKH. This. And now from here, you get this as this one. In N1 to N3, I mean 1, 2, 3. So this would correspond to the second property. This would correspond to first one, and this is the third. This one and this one get cancelled. And this and these things cancel each other here. So you are left only with the OH small order H terms. That's down. The three of them, one coming from here, one coming from here. All those together are also small order H. In other words, in this summation, the contribution from this guy is going to be very, very negligible. Note it down. Yeah. So again, use those properties 1, 2, 3. So for each of these objects here, for each of these things here, this, then you get the first object is going to be mu I times h times that other thing. This one, this is going to be mu I times h plus small order h, and similarly, this will be lambda I times h plus small order h, and so on. So again, using verify that. Right. This is an exercise again for you to verify. Oh, there is one small thing. There should be a bracket here. This bracket because Pij times 1. See here, this object, what we are writing in that close to that bracket thing is this. This remains outside. Okay. So put a braces corresponding to this. There should be a bracket here. So what you should have here is that Pi 1 times Pijt. So Pijt minus this term. So that here you get Pijt times 1, and that you take it to the other side. You take 1 multiplied by this to the other side. And then divide by h. So this h gets knocked off, this also gets knocked off, and this also gets knocked off. So you have this. And then you have OH small order h divided by h. So now let h go to 0. So here you will have the derivative of Pij t. Derivative of Pij at t. And these things, they are now not depending on h, and this goes to 0. Please note down. So we'll go to the next slide. Yeah. So letting h go down to 0, decrease to 0, one obtains now a differential equation in t. T is the variable, t greater than 0. For every j greater than or equal to 0 and I greater than or equal to 1. And consider the case when I equal to 0, then that I going to I minus 1 is not possible. So a similar argument will give you this. You can verify this, okay? So since mu I will not, that this whole thing will be missing. And here again, this will be missing. And you have correct. Of course, the initial condition Pij 0 is delta Ij volts. So we have the following result, an important result. This theorem says the transition probability function of the birth death process satisfies the following system of ODEs. This system we denote by spade. I think, not in my notes, I had a spade for this. Yeah. I had denoted, I think, club suit, I mean spade suit. Also that symbol somewhere here. So, with the initial condition. So this is J is fixed here. So you remember in our arguments, J is kept fixed. The I only is changing. Here, for example, I minus 1 comes into the picture. The J remains the same. Similarly, J remains same. Similarly, J remains. For these things, we have got from you are using the hypothesis, the postulates of the birth and death for these. Yeah, J is kept fixed. So I can vary in the argument. Yeah. For a fixed J, when I equal to 0, it has this. That is the second equation we have. And for I greater than or equal to 1, we have this with the initial condition. So this system of ODEs is called backward Kolmogorov differential equation. Please note it. I will presently explain why this adjective backward. Yeah, please note it down. Yeah. So when we derive these things, first of all, notice that we had decomposed the time interval 0 to t plus h as 0 to h and h to t plus h. And J is supposed to be the state at t plus h, the state at which the process has reached at the last time point in this interval. So that is kept fixed. And the initial state is J can also vary in our analysis. See here. Whereas J remains the same. So sort of figuratively, it says something like looks backward in time, namely it is something like In an ODE, the terminal value you give, and you have to determine the solution. You know, in many ODEs, you have seen that if you know the value of the solution of the differential equation at one point, you can construct like that. So naturally, the question is, instead of backward, why not forward? Which means here you take it 0 to t and then t to t plus h. One can do that also. In that case, this guy I would be fixed and j will act as a variable. So that in that case, one can have looking forward in time. But the price one has to pay is that it requires an additional condition for the analysis to go through. And also you will see what differential equation one gives. Okay. See, the problem here is, yeah, in this case, when we consider the backward equation, we could easily prove that this is negligible. So when you consider the other way, 0 to t and then t to t plus h, it doesn't happen so easily. That is why one requires an additional assumption. So assume here that for every j, if you take 1 over h times pkjh with k not equal to the adjacent states or the state itself, namely k not equal to j minus 1, j or j plus 1. So one has to assume supremum of k varying over this of pkjh is small order h. So in that case, the transition probability function satisfies the following set of equations. Here I is kept fixed, and this corresponds to when j is equal to 0. Notice the differences in the forward and backward equations. So Pi0 prime t is this minus lambda 0, Pi0 t mu1 times Pi1 t. So here, even here, the j is very, I is fixed. And similarly for this. So there are equations backward and forward. They are equations in different variables. This is an equation connecting the initial value I and t. Rather, that is sorry, j and t are kept as variables. Yeah. I is kept fixed. The initial point is kept. Whereas in the backward thing, it was the other way around. Here I is kept fixed and j varies. Yeah, we will briefly sketch the proof. Very similar. Yeah, first note down the result. So in general, this forward or backward system, in the general setup, it may be difficult to solve. We will see some specific examples. Go as before. Only thing is, first step, you decompose 0 to t plus h as 0 to t and then t to t plus h. So this corresponds to this thing, t to t plus h, the dynamics or the evolution during t to t plus h, and using time homogeneity, this gets simplified to this 0 to h. And here corresponding to k equal to j minus 1, j and j plus 1, take out those terms, and the things which, the remaining terms. So because of our additional hypothesis, this guy, it is less, each of this is less than, and here none of the k, these things are involved. So therefore, by our extra hypothesis, each of these is dominated by the supremum. And then the remaining. This sum, this is a sum over I. This is less than sum over this object with k running over all these things. But that is a transition probability function. So that sum would be 1. So therefore, this object is dominated by 1. That sum. So this whole thing is now dominated by just this object. And by our additional hypothesis, this precisely is small order range. Therefore, you go back to this thing, then you can write this as these three terms plus smaller. Now proceed as before. In spirit, the same as the earlier situation. So if you let h go to 0 now, then you will get the second ODE in the club suit equation. This equation. That is the more laborious part. So a similar argument will also give the thing when j equal to 0. So the forward equations is generally intuitively the more natural. The backward equation is technically more convenient. And even for other types of processes, many other processes or class of processes, the backward differential equations will involve less assumptions. Whereas the forward equation will generally demand bigger assumptions and sometimes smoothness properties and things like that, which one may not need in the backward. And in the context of Brownian motion and diffusion processes, more complicated processes, the backward operator and the forward operator, when a lot of technical conditions are satisfied, will turn out to be the adjoints of each other. Adjoint in the sense of what you see in functional. So the forward operator in general will demand greater regularity assumptions on certain coefficients involved in the setup. So this portion, this completes what I wanted to say this week. These things I hope to put it up. Next week, I am very doubtful if I would be able to take classes. So that thing I will write it up and put up the notes due course. So if you want me to go back to any of the slides, I will be happy to do that. Yeah, otherwise I will stop sharing. And okay, take care. All of you here means 2 of you. And we will see you later. Okay, take care.
Thank you, sir.